Hi guys, and we're here for our fourth and final video on classification for text. In this one, we're actually going to get to do the fun stuff where we figure out how to fix our models and a little bit of deep learning. So as a reminder of what we were going over last time, we had looked at several different models. And so we used tf-idf to make a feature extraction, and then we were printing our classification report for logistic regression, Bayes, and support vector machines. And I went on a small but important rant about how you need to really pay attention to each class precision and recall, because then we would miss this problem that there were zeros if we only focused on accuracy. Right? So accuracy is very, very handy, but in digging in, the most important component is to look at basically each individual accuracy as well. Okay, if all models are created equal, the one with the accuracy in the kind of best scenario of precision and recall is a good model. Okay, so these were all crap models because they never predict P5, right? So this is a class imbalance problem, which we also spent some time discussing. A model that never predicts one of the categories is no good. Okay? So what we can try is called undersampling, sometimes called downsampling, where we sample from the larger categories to get closer to the smaller category, which works really well in this case because we have one category that's much larger than the rest. Oversampling, sometimes called upsampling, is where we create new artificial or repeating the smaller categories to match the larger category. Largette is not a word. I swear to you, my RStudio spell check sometimes does me dirty. Okay, the larger category. And I don't know that I recommend oversampling too much, because one, if you're repeating instances, that might represent reality or it might not in a small case. And making up artificial ones, which is very popular right now, could be good, or it could be misrepresenting the frequencies at which those particular text components are occurring. Okay, so I usually recommend starting with undersampling, especially if you already have a big data set. So what I did here was I just grabbed a data frame where the priority was P3, because that's our largest category from the beginning, and grabbed about 4,000 of them. So I still made it bigger than our smallest category here. And so I'm not necessarily grabbing all of them where there are 252, although I could do that. I'm still leaving it where we're getting that ratio of the different prior probabilities in play, but you could also try sampling where they're all just much smaller as well, where they're all equal, for example. So then I created a separate data frame that didn't have P3 in it. So I've kept all of them except the extra examples of P3. And then I threw those two back together. So now I have a much more balanced sample. I still have two that are much larger than the rest, but the balance isn't quite as bad. Also, it's still pretty bad between P5 and P3. So we're still going to have a very hard time predicting P5 if there's no good markers for it. And so we could try this again with even, bring the numbers down even more. Okay, the problem with undersampling is that you are losing information. So this is all the same as before, but now with my new data set, my df balance data set. So all of the code's the same. We've got x train, x test, y train, y test. Remember, the first one needs to be x, the second one needs to be y, if you're going to put them in this order. Y here is our category labels. Our test size, 20%. Random states, we get the same random sample each time. So for reproducibility of our run, and we're stratifying that sample based on the Y variable. Okay, so our training data is about 7,000 and our test data is about 2,000. Okay. I do have to extract my features again because now there will be features that have been dropped because they were only in those examples that we've dropped. Okay. And remember, the big key here is to make sure you use fit transform and then transform, and the shapes need to have the same second number. Okay. Now, did I not do log? I guess I only did one of them, but we trained the model and we see how much better we did. Okay. Now, overall accuracy has gone down because we've actually started to predict things better, which seems weird to say, but remember that chance is 20%, 1 out of 5. Okay. And so what we're seeing is instead of just getting all of P3 right by guessing everything in the P3 category, we're actually starting to get some of the other ones right as well. So it seems like the model's getting much worse because the accuracy is decreasing from the first model, but the first model is not usable because there are some categories we're not predicting at all. And this model is still not good. It could get much better. It's better than chance, which 20% versus 50%. And that might be a good start. And then we could start playing with the different categories. Right? And since I have this data open, let's see here. If we also test some of our other models, what happens? Right? So let's go back to log real quick. Train the model log. Okay. Since our names are still the same, I can just kind of rerun it on the second data set, I think, and see what we get. Okay. Oh, I didn't like that. Iterations. Oh, yes. So I should probably increase the amount of iterations because it says it didn't meet them. So we could say max iter, I believe, 10,000. Try again. And that may take a little bit longer to run, but now it's much happier. It compiled. Okay, I didn't like that. I'm not sure why. So let's look at our model assessment on this new data set. Okay, or maybe that's not running on the new data set. Let me see what I did here. Okay, so we made our DF balanced. I called it X train and X test again. TV train. Okay, so these should be also on the new data because I cut and pasted. So let's see, test, too much scrolling. Confusion matrix on our log. That looks good. So let's go back and look at log. Okay, so logistic regression is still not doing us very good. Oh, the accuracy has changed. So we are doing different than before, but we are starting to get some of them right. Okay, but none of P5. So SVM is doing better. Let's look at Bayes. So even knowing those prior probabilities, we're not getting 4 and 5. So I think SVM is probably our best option to continue to tweak the model, right? So it's still not doing great, but maybe we can try a different feature extraction or try turning the class balance issue down even more. Okay, so we can try that real quick. And that one I can do a quick and dirty, I think. No, my students know that I'm not very good at pandas on the fly. So what we would do is do tf-sample. So now we want to do group by. Priority. And then we want to do sample in equals 252. I can't remember if this is going to be group by or group by. I do way too much dplyr. Okay, so now they're all 252. Okay, so what happens to our SVM model at 252? So they're all equal now, which is maybe not the best example because we're losing a lot of information, but can we predict better? So accuracy drops even more. So no is the short answer, right? So accuracy drops even more. And so we're getting more of them right within each category. Okay. Although that's not good because what's happening is we're getting less of P3 right because now that it's not so heavily weighted in the data set, we're having a harder time distinguishing between the two. Okay. So from there, what I would try is a more balanced sample, right? But leaning into still the difference in the prior rates for the sample, and I would change feature extractors and start playing with that component of the pipeline. Okay. But since I had it open, we could do a little bit of this on the fly. So if I wanted to change feature extractions, I could, because I mean, tf-idf and bag of words are not that different. I mean, mathematically and inside the number frame, they're different, but like conceptually, not really. So what could I try that's different? Well, I could try using a word-to-vec model to see if I can capture some of the context to predict these categories a little bit better. Okay. And so this is our flattening function from word-to-vec. And what it does is it just takes that model and helps flatten out the frames in it. And we talked about this in the previous lectures, where it will sort of average down the multiple context vectors to create a a document by dimensions matrix. Because I need to continue to have documents because that's what I'm trying to predict, but now I get the dimensions based on how many ever I put in there. And remember, dimensions are meant to represent more of the like underlying thematic context representations in the text. So I'm going to import word-to-vec, and I'm going to do this just like we did in the like 2 videos ago. So we put in our X training data set, okay, and maybe not super clear. That we needed to X train needed to be tokenized. Okay, that's going to be many slides back. Okay, put in our vector size. So I'm going to do 10 dimensions, which is not very many. Okay, and see what I can get out of 10 dimensions. Okay, our last model was predicting with 35,000 predictors, so I don't know how much better I can do, but there should be less dimensionality in this data. Now I can certainly, increase this up. Okay, 5 window size, so 5 words on each side. A SIBO model, although a skipgram model could work just as well. Min count, the number of times a word has to appear to be included in the vocabulary, is 1. Okay. Workers equals 4. Okay, so after you build that model, you would use your flattening function to put the documents into the right format. So now we've got documents by dimensions. Okay. I'm going to use the same SVM model. So I put in my training features, put in Y train. I test it by predicting my test features and print this classification report, and I do get this giant warning. It's really bad. Okay. It's pretty bad. It never predicts, even on a more balanced data set, P4 and P5. Okay. It is getting a lot more of P3 right though. So potentially that's because we are only using a vector size of 10. So let's look really quickly on what size these are. Okay, so it's only 10 predictors. Potentially that is not enough. So just for fun, because this data set is not super huge, let's just say 500 dimensions. Okay, let's give it a lot more room to move around and create differences based on the context in the text. Okay, now a larger corpus is going to take a lot longer to train. So for example, I was running one on the entire Wikipedia dump for Thai. It has like 96,000 documents, which isn't really that many, but that took about an hour to build a fast text model on a medium-sized virtual machine. So they can take a long time to run, but once you have them run, you can load them and unload them, that kind of thing. So they're really just problematic to build sometimes. Let's see, do we get any better? Yes and no. So the prediction goes down for some categories, but up for others. Okay, so we get up to 34%. But the prediction is actually much better across the board versus a minute ago. Okay. So, you know, just for fun, let's try a larger window size. Now, humans cannot do this kind of window size, but let's just try larger context windows. Okay. There is a more systematic way to do this. I'm just kind of showing you how inputs and outputs can really affect the results. Okay. That didn't do a whole heck of a lot, right? We're getting maybe 1 or 2% better. Okay. So it's maybe not the window size, but the vector size. So I'm going to upgrade one more. I'm not sure if I can have more dimensions than documents. I guess I can. Okay. I don't know that artificially continuing to increase dimensions will always work, but you know, so that it's diminishing returns. 500 gave me a pretty good bump. 1,000 didn't give me much change. Okay. So we'll leave it at 500 for these notes, because it does at least do something good for us. So I might go back to tf-idf and then keep playing there. Or it might be that this data set's just hard to predict. Or we could try some deep learning. I sort of always tell students to approach this last, because these models are computationally expensive to run. And when they break, you have no idea what's going on. So they are really handy, and they can be trained to do things with the careful analysis of if the return is worth the investment. Right? So 2 of the most common options for text classification include convolutional neural networks, or CNNs, and recurrent neural networks, or RNNs. And when you see people talk about long short-term memory models, those are usually RNNs. Convolutional models have connections between all the layers and all the nodes. Recurrent models, or long-term short-term memory models, have like kind of a nice hold on previous context. So it's kind of like a short-term memory of what the model just saw last. And so I'm going to show you how to prepare the data for either type of model. We're going to use Keras and TensorFlow for this, which are easily the most popular packages. You're really using Keras, but you have to have TensorFlow to make this work. Okay? And so to do that, we're going to tokenize the text, nothing new there, and convert them into word index vectors. That is new. Okay? All of the sequence inputs into a deep learning model have to be of the same length. So we are going to make them all the same length by padding them. We're going to map those word indexes to the embedding vector, which is effectively what word2vec does when it maps, you know, 10 words at a time or whatever. Okay. And then we'll use that output into either model. So the nice thing is, if you can get the output in the right format, which we've talked about, you know, different packages and functions want different formats. So if I can get it into the right format, I can use it for either model. So that's cool. All right, all this stuff, so much stuff. And I don't think I actually used 2 categorical. It wasn't working properly. But what we're going to do is use Keras tokenizer and Keras pad sequences. We're going to use some different types of layers, like a convolutional one-dimension layer, embedding layers, long short-term memory layers. We're going to use a sequential model. So sequential models run one layer at a time. Okay. And so let's see here. Our max sequence length will be 1,000. Max number of words total 20,000. Embedding dimensions 100, and validation split 80-20. Okay. Why those? Book suggested it. Okay. A lot of the numbers here feel very arbitrary to me. And I think, you know, when I've been reading, I'm like, well, why 128? People are like, it works. So there's a lot of those kind of like implicit rules or implicit starting points that tend to run. Okay. All right. So we're going to use the tokenizer from Keras. The number of words will be our max number of words here. Max number of words. Okay. And that tokenizer is fit on the training data only. And what that means is that the out of word problem still exists, okay? Or out of vocabulary problem still exists. And so we say, okay, here's our tokenizer, build a blank model, max words, 20,000, okay? Fit it on the data. Okay, so the structure is very similar. Build a blank tokenizer, fit the data to it. Our training sequences are tokenizers to sequences on an X train. Our test sequences, tokenizers, text to sequences on our test train. That was a whole lot of text and test, but we're building our training sequences by applying our tokenizer to them that have a specific, data fitted, right? So we fit it to the training data, and then any words in the testing data that weren't in the training data, gone. Okay. Our test or sequences are where it's converting this into those word indices. So word. Okay. That's why I use the tokenizer. And then our word index is tokenizer.word index. So there are 34,000 unique tokens. This is just how long it can maximally be within a document. All right. Max sequence length is 1,000. Okay, good. Our training data, our training validation data, okay, pad sequences. Okay, pad sequences just make sure that the length of each sequence is the same. So it'll basically pad them with blanks when the sequences aren't long enough. Okay, so I would use a smaller sequence length when you have smaller texts. Okay. So our training validation data, pad sequences, you put in your train sequences, test data, pad sequences. Okay. Our labels, this is what I changed. There's a to categorical in Kara's, but it was not happy with me. But pd.getDummies, so it converts the label column P1, P2, P3 to what's sometimes called dummy coding, but this is a little different than regression dummy coding. It's effectively a one-hot matrix. So for each document, there's columns P1, P2, P3, P4, P5. And if it's P1, there's a 1 in the P1 and zeros in the rest. It kind of creates like a binary code for each one, because the outputs need to be ones and zeros as opposed to categorical labels. So you got to do that to both data sets. This validation split, so we're going to create a training data set and a validation data set. So internally in a lot of these models, there's like training, a validation, and then test data. We could have done that with our logistic regression and the other models, which a lot of people don't. But embedded into deep learning models, you have the training and the validation data as part of step one, and then you have a separate testing data. This is kind of common practice. And so this bad boy here splits that data up. So our training and validation data is also split into an 80-20 split. Okay. Now it will learn the validation data. So that's why it's so-called train validation. So it does learn those data points. So you are getting to see all of the vocabulary words from it, and it does get to learn them. But it does give us a information as it goes about how the training is going. Okay. Then we program the model. Okay. So minimally, deep learning models need to include an input layer. Surprise. Okay. And for us, that's going to be an embedding layer. We're not going to use pre-trained embeddings. We're going to embed our own data. Some sort of hidden layers. If it's only one hidden layer, it's very close to a word-to-vec model, but some sort of hidden layers. And some sort of output layer. Okay. The most common thing that text folks use is called softmax. Okay, that's also what word-to-vec uses, where the output is a categorical class label. So which column would it be? P1, P2, P3. Now, what hidden layers you use and in what order is magical learning from examples. I don't know that I have a good answer for why this layer then. Okay. Other people do, and I suggest reading different ideas, but there are a lot of similarities you'll see between models, a lot of people's trial and error, right? And so I'll show you the most common setups for these models. Okay. So a convolutional neural network is going to use hidden layers of convolution and pooling, okay? Hence the name. And so in text classification, CNNs learn kind of bag of words information. Okay. So using that sequential model in Keras, we can stack together hidden layers that run in order. And we need to define 3 components in both types of models. So we define the optimizer, the loss function, excuse me, and the metric in which the model is hypertuned. So remember, hypertuning or hyperparameters is just like tuning the dial. So it's getting feedback about when it's getting it right or wrong with the validation data, and it uses that information to update the weights. Okay? Because these are iterative models as opposed to logistic regression, which is a closed form solution, meaning there is one mathematical answer. This is a model that kind of tweaks itself as it learns. Okay? And so hypertuning is that process, and we're going to tell it how to do that. Okay? So why all these layers? I took it from the book, 100%. And so I could try it without maybe so many, maybe just one. So I could get rid of one of these stacks, for example. But what's going on? So we've got a sequential model. So you start by saying, I'm going to run a sequential model. These steps are in order. Okay. You got to have an embedding layer, or who knows what's going to happen. So this is our input layer. It's an embedding layer. We've got our max number of words, and this is how many notes. Okay. 128 is a very popular number. I feel like there's some like computer science nerds out there that it's like 32 bits, 64-bit, 128 bits. It's my guess. Okay. Add a convolutional one-dimensional network with 128, so you got to make these numbers match, right? 5, why 5? Well, we've got 5 answers. Okay. For this activation, okay. ReLU activation, I'm gonna have to look that up. Can't always remember what it stands for. Okay, rectified linear unit. Okay. And so if you know anything about how the brain works, I mean, it's frustrating because these models they're kind of like loosely inspired by the way the brain works. They're not really like meant to mimic the brain like we used to kind of claim they do. They're sort of like inspired by brain stuff, right? So we can, there's a nice, looks like what's probably a nice blog on this, but if I understand this correctly, it essentially is very similar to like it's either on or it's off. Okay, so there is like a period of like off and like, oh, and then it's on. Okay, and that's hence this picture here. And so let's see kind of what it says. Piecewise linear function that outputs positive, otherwise 0. Yeah, so like as you go across time, it's like do do do, nothing on. Okay. And that's very similar to neurons up here, because they either fire or they don't. Okay. So that's how it's telling the nodes to come off and on. Okay. Pooling is where it sort of like pulls all that information from all of those points together. Then we do it again. Okay. Give it another convolutional network or convolutional layer where we have everything sort of turning off and on, and these are hidden layers. So I couldn't tell you what any particular node does. It's just helping mathematically tune the model. Then we pull it, okay, add one more. Why 3? I don't know. I really don't. I think we could start with 1, see how well that works, and then try adding another one, see if it improves your model. Global max pooling is across everything, right? Now, most people add dense layers at the end, especially for the output. So a dense layer connects everything to everything else. And then our last one here is the output. Okay, so it's a dense layer. Notice here that the shape is based on the amount of outcomes as well up here. So there are 5 outcomes. But I forced it to map onto whatever the code says. And the activation here is softmax. Okay, it's taking all those probabilities and picking the most likely one, like word2vec. Right? All right, now we've built the structure of our model. Let's do it. So .compile. Okay, our loss function, categorical cross entropy. You'll also see binary cross entropy when there's 2 outcomes. So categorical cross entropy calculates us getting it wrong based on having multiple answers. So loss is a measure of how much the weights are changing with each round. So you want loss to sort of level out, okay, get close to 0. Before you stop training a model, but you don't want to continue to train after loss essentially becomes 0 because then you're overfitting the model. Okay, so categorical cross entropy is very popular for models with more than 2 outcomes. And I actually don't know what this optimizer is. Oh, Karis is going to tell me though. Maintain a moving discounted average of the square of the gradients. That's some math. I like math, but it is one of the many options, right? So let's see. Let's look at what our other optimizers might be. I've seen a lot of people use Atom. I usually am more partial to Atom. It's a stochastic gradient descent method. It does tend to work pretty good. If this wasn't slow as heck to run, we would try it. But you guys don't want to sit here and wait. So there are a bunch of different optimizers that you can pick from. And I don't know how much they're going to make a difference, but there are obviously different types of math that will potentially change the output. Unfortunately, this part runs very slowly, so I won't show it to you now, but you can take these notes and change it to Atom if you want. Okay. What metrics should we tune on? We're going to tune on accuracy. Okay, we would like to get the answers right. Okay. There are other ones that you can tune on as well. I could tune on val accuracy, which you'll see in a minute. All right, so I ran 5 epochs. That is not epochs. It is not enough, but I needed these notes to knit. Okay, so we built our blank model. Well, it's not blank. We built our model, right, with all the structure, and then we're going to fit it. X data, Y data, batch size, epochs 5, our validation data, X val, Y val. And so you can see batch size controls how many components it's getting at once. So there are 48 batches within each epoch. Okay, and that's due to how many training examples I have. Okay. And then we get answers out here. It also tells you how long they take to run. And so it's not terribly bad, I guess. A couple seconds for each one. We can look at our loss. So let's watch our loss. It's going to go down, go down, go down. It will bounce up and down. And there's some cool packages where you can get this to make a pretty graph for you. Go down, go down, go down, go down. This model is not learning very fast, right? So we end on 1.14. Definitely needs more training. Okay? But who's got that time to knit the notes, right? And now our accuracy is continuing to go up. So that's good. So we'd like to see our loss continue to go down and our accuracy tend to go up. However, it's not really like pushing much past the 43% range. So we may not get much better than that. However, that is better than some of our best models that we had where we're actually predicting each category. Okay. Now our validation loss and our validation accuracy are very similar. Okay. And that's a pretty good thing. Okay. If our accuracy on the training data and then our accuracy on the validation data are very different, that implies that our model maybe can only learn the training data because it's getting the answers and it can't learn the validation data. Okay. So what would I do? I would run this model. Oh, it does actually get above that. It gets to 51%, which is pretty good. I wasn't looking at the last one. So I would keep running the model, give it more epochs, and see what I could get to. So I watch loss slowly decrease. and make sure I don't train it too long. All right, then we would test it. Can I scroll? There we go. On our test data. Okay, so completely different data set that has never seen an answer for. So we do CNN model dot evaluate instead of fit, test data and test labels, right? And it will run in batches as well, based on the previous stuff above. And it actually gets the first batch pretty good. But the average accuracy is 51%, which is very close to our final accuracy from the first model. Okay. So do I think this model could learn the data? Yeah, I do. I think it could. Could I get to something really high? I don't know. Now, again, if I were doing this for real and I wasn't just trying to make the notes work long enough to run, I would test it with a lot more epochs and see what happens. It would be bad if I could get the accuracy like 90% on the training data, but then on the test data only get it at 50%. Okay, that implies that it doesn't actually generalize to new data sets. Okay. So loss is the amount of change occurring in the model across training. Loss is only useful compared to the same model being tested. So it's only useful number like compared to other runs. And so you want to make sure it's going down, because one model might start at 6 and another model might start at 2. And that doesn't imply anything except that the first model is changing a lot, but they might not have the same metric, the same scaling. Okay. Val accuracy is our validation accuracy, right? We can use that to help determine if our model is getting better. Overall accuracy on a new test data set to see if it generalizes. Okay. And generally, you want to use at least 10 epochs or more. Okay. I feel like the choice of layers and settings is fairly arbitrary. Other people may feel differently, but it seems very arbitrary to me. Most of the time when I see examples of these things, like, let's add this layer. There's no reason why, other than let's do it. So I would do some background research on the type of thing you're trying to predict and see what other folks have done successfully and start there. So let's try one more, the long short-term memory example. And they're very popular in language text stuff. Okay, CNNs are more popular, I think, in picture prediction. Okay. Because they're sequential and they have memory, kind of like we do. Okay. It does embed context, and it uses the exact same inputs that we've already built, just a different model structure. Okay. And you can actually mix these together. There's nothing that says that you can't run a convolutional model with a long short-term memory layer. Okay, those are LSTMs. Okay. So I'm teaching them as separate things, but they're not necessarily separate. Way fewer layers here, but we'll have a sequential layer. We got to have our embedding layer, and we got to have our dense layer. Okay, and all we're gonna what the heck? All we're gonna add is a long short-term memory layer with some dropout. Okay, dropout just means you forgot something. Okay. Again, 128. It's just really popular. All right, I only trained this on one epoch because they're slow as heck. Okay, CNNs are a little bit faster, but oh man, this bad boy was gonna take an hour to run more than one. Like this is 3 minutes for one batch. Okay, so it is quite slow, I will warn you. But in one epoch, it gets up almost to the point that previous model got up to in like 4. Okay. So I do think it would be pretty predictive. And so if you want to compare these two and you got some time on your hand, change both of them to 10 and run the notes. And then let's look at our test data. If I can get the model to scroll. Whoops. No. I don't know what I'm doing. Escape. Back. Sorry. I was trying to just get the thing to scroll. There we go. Very similar accuracies. So it is still at least predicting the data in the same way. Okay, that's a good sign. All right. So those are our 2 brief forays into deep learning, But again, I wouldn't do them unless necessary. Simpler models are cheaper, easier, and better. Okay. Now, a lot of times in business contexts, especially, or more practical contexts, you need models that work. For whatever you're doing, you just need something that works. But what if it doesn't work? Right? Like this example, it's not really working that well. What should I do? Or the model stops being useful. You realize that the model's not really predicting in a way that helps you, your business, the people you're selling this to, etc. So better yet, and someone mentioned this to me, so GDPR is a data protection used in Europe and I think in the UK, that is meant to protect participants, humans, and their privacy. Okay. Now, I use GDPR a lot because it's important when I collect human data. So I work with research teams all over, and I have to make sure that I'm following the rules for this. And I do think, I can't remember if this applies to data algorithms at the moment or if they're trying to add this component to it, but either way, if there is a question about the biases present in the model due to the data used in it, you would have to tell someone how the model works and what the model is doing. And this is a big area right now that I feel like data scientists are like, whatever, as long as it works, who cares? And I'm like, a lot of us care. A lot of people want to know, well, how did you come up with that ability to tell me I should get a loan or not? Okay. And they're like, oh, it's a formula. Well, what goes into that formula? What data did you put into that formula? Why? How does it predict me? You don't have any data about me. Okay. Or people do, but so like our understanding of what the model's doing can be very important. I think it's important on our end to make sure that there aren't biases that we're sort of unaware of in the data. And then like practically legally, it could be an issue too. So what do we do? How do we interpret that? Okay. So we could look at all the probabilities embedded in the model and look at which predictors are best. So look at the examples that are being predicted the best. We're getting them right, the most right, so to speak, and see what that tells us. Okay, we can use Lime, which is a cool package that helps us explain models. Find Lime a little bit tedious, but it's pretty cool. ELI5 is much faster, but that doesn't have as many features. Okay. And then there's one more, and I can't remember it, but we'll find it in here. Okay. All right, so I ran the logistic regression again because SVM can be a little grumpy with Lime. There are ways to do it, but it could be a pain. So I ran my bad model, and you can see the model's still pretty bad. Okay. Now, to get the prediction probabilities, and so you can get the prior probabilities out of Bayes, the prediction probabilities can come out of log. If you want to use SVM, you can convert them into prediction probabilities, but you need to use linear SVM specifically. Okay. With log, it's really easy. You do log your model dot predict proba. Okay. And I've converted that into a data frame. I've added the answer back to it and the test data back to it as well, and predict the original predicted categories. So let's look at that. What is it called? Probs. I left myself a note. Look at the data frame. Okay. So we have our prediction probabilities for each category. So this first one went into P3 because it has the highest probability. The actual answer was P4. I got my literal text and a predicted category. By having this, I can now create a data frame called right answers, where I say, okay, only show me the ones that I got it right. Okay. So these are all correct. And what I could do is sort. So let's say, okay, I want to look at P1s, and I'm going to sort by P1. And these are the ones that I predicted the best, okay, because they have the highest prediction. Okay. I'm getting them right the most. It's kind of a weird way to think about it, but we could look and see potentially what is happening. And so NPE is coming up a lot in just this one sort. I don't know what that means in this case, but that might be a good clue. Let's look at P5. Okay, now P5, I'm getting none of them right. Okay, so I can't use that one. Am I getting any P4s right? Yeah, a couple of them. Organize, delete, revert causes error, smoke. Okay, I'm not sure if I'm seeing it here, but you know, in your own data, you could probably learn a little bit better. It does seem like it has a lot of these little codes, but that might be true across a lot of them. Okay. So it literally requires some digging. Print it out, just look at it. Okay. Now I could also use the coefficients. So logreg.coef.shape. So there are 5 coefficients for the 5 categories, right? Or 5 prediction whatevers, and I have a coefficient for each one of my words. And so if I do tf-idf.get feature names, right, that would be all of the literal words, because in the model they're not coded as words, they're coded as like coefficient 0, coefficient 1, coefficient 2. Okay? So these two match. Now I can add the coefficients to that data frame we were looking at a minute ago by transforming them. Okay, so .t means just transpose, sorry. So we're taking that coefficient data frame and just turning it this way and giving it labels. Okay, then I'm adding the words to that. So let's look at that. All right, so the strongest negative predictor for P1, okay, that means if this word is there, it is not P1. Okay, if it's there, it's probably P4, would. Okay. Now we probably should remove a lot of these words. Okay, so we didn't remove for this model. It doesn't look like we took out stop words. Okay. So that's potentially problematic. We should do that. Okay. Now, when you're embedding context, you probably want stop words. So in this case, we probably should have removed stop words. Now let's see. If I want the highest predictors of P1, it's a code. Breakpoints might be a really good one. MPE. So my visual inspection matched what the results are. Hit, results, launch, evaluation, workspace, scrapbook. Now let's look at P2. The highest predictors, RC1, M4. So now I'm starting to figure out there are certain categories that go into certain priorities. Now, if you want a more visual way to do that, you can use Lime. Okay, I like doing it overall. Explain it like I'm 5. We'll do this kind of model sorting for you. But Lime allows you to predict new instances, which is nice, and individual instances in the data set. Okay, my beef with Lime is that it does one instance at a time, meaning one text. That's a little slow and pretty tedious, but you could look at the best predicted examples to see what the predictors are for those. Okay, so it's called local interpretable model agnostic explanations, which is a lot of words. Okay, and so it's useful to know which examples are the best one. I remember those would be ones with high probability probability values from the output model that you're getting right. Now to do this, we're going to use scikit-learn's pipeline function. So make pipeline our tf-idf and our logistic regression. So you put in your feature extractor and then your model. Okay. We put in our, to predict a new instance, we would say pipeline.predict probabilities so that we get those probabilities out like we saw a minute ago. And if we put in compiler not working, okay, and that would be an example of what a bug might be. Okay. It says it's probably P3. But then to get the Lime part, this did not print. Oh, it did print properly. It just looks weird. Okay, so to get the Lime part, what we do is go from lime.lime text. Okay, import Lime text explainer. We're going to build an explainer. Our class names are what, like P1, P2, P3, P4, P5. Okay, I'm just pulling it directly from the model, so I can't mistype something. Okay. We're going to pick a random ID, and I think this is one of the IDs that we got right. Okay. And so you can check that. Right answers.iloc. Okay. Right answers.iloc of the answer. So our predicted category is P1, our true class is P1. That's just making sure I'm pulling one that I'm predicting well. And then I printed the actual text. So this is actually what that person put into their bug. Okay. It's got a lot of action going on here, but it does have NP in here, which probably is going to be one of our best predictors. So to do that, to look at the predictors and make this cute little graph, what we do is they say explainer.explain instance. You put in the text, the probabilities, and the number of features you want to see, so you can put in more. To get it to print out in RStudio and Jupyter, you can do as pie plot figure, and it'll print out this. So for this exact example, the predictors, if it has these words, org, Java, views, UI, and action, it's more likely to be this example. If it has these words, it's going to move it away from this example. So these negative ones mean if those words are present, it's going to say it's probably not that instance. Okay. So Eclipse, internal, et cetera, et cetera. Now, I like doing this version better where we save to file. Okay. And it will save in the same folder as whatever you're running this in. Okay. And so we're saying it's not P2 and it is P2. I thought we were looking at P1. Okay. I guess this particular one I picked is actually P2. Did I do something wrong? I did ID value, which is odd because the answer is P1. Okay. I'm not totally sure about that because it does not, unless my randomization is different, at different times that I've run it, because it's not even the same text. So this particular one looks like it probably should be P2, but it got classified as P3. Okay, so not the right answer is the right answer, right? And it printed out and it does this cool coloring too. Okay. And so it's got the positives and the negatives. I don't know why they don't match for what I had over here. It's probably something quirky with my setup. All right. So for explain it, but the problem with Lime is you got to do that one piece at a time. So I'd have to do 5 or 6 for each one to really, each category on the top and the bottom end. Okay, so ones that we're getting really right. And I can also look at ones that I'm getting really wrong. Okay. Now, explain it like I'm 5 also we'll do overall. This is very similar to us getting those coefficients and printing them out. It's just a like quick and pretty version of us instead of us like, oh God, coefficients and making all these data frames. So show weights, estimator, our log regression, feature names, get feature names out, and it will print them out for you. So it printed us the absolute value. It's unfortunately like colored very poorly, so let me highlight it. There we go. This is the top 10 absolute value strength. So you've got more negative ones in some other places, but we can see which the top ones are: NP, scrapbook, and the bottom ones are C1, back, M4, warning, notes, compile, write bugs, and it does keep scrolling actually. So it does show you all of them at once. So this is really nice because it shows you the top and the bottom coefficients for all of your categories across the entire model, instead of looking at one at a time. But if you're wanting to understand ones that you're missing, so you're getting the answer wrong, you could redo this line, but look at ones where the answer isn't right, instead of looking at ones where the answer is right. I actually recommend looking at both. All right, so let's wrap this bad boy up. So across all 4 lectures, we've learned how to create classification pipelines, taking those feature extractions from the first 2 lectures and applying a couple of different classifiers. We learned 3 different classifiers: log, Bayes, and SVM. You learned how to assess a model. This is using precision, recall, and accuracy. Okay. You learned how to deal with class imbalance with undersampling. You saw a couple of examples of deep learning models that you can take and tweak and try on your own. Okay? You learned how to extract the predictions, the coefficients, and information about what the model is doing to help yourself understand what's going on, especially if the model stops working and starts breaking. Okay, so a whole host of things. Essentially an entire semester is a week machine learning crammed into 4 weeks, but this should get you started on predicting text and learning how to tweak and build better models. Okay, we're going to end the semester on chatbots, which is like text prediction on steroids, and then you will have learned a long list of NLP tasks that you can apply in many different scenarios.